All right, welcome back. So here we are, we're chapter 9. Now, in chapter 9, we're going to deal with lists. Now, we've dealt with lists, it seems like forever now. And this is not going to be just the traditional lists. We're going to talk about other types of lists and how they come into play relative to the different data structures. So, we've talked in the past about other structures that use lists, stacks, and queues, but we're not limited to just lists. We can also use arrays for that. But for what we're dealing with, um, lists, arrays, they're going to be very similar. The main difference that we've talked about in the past between the two is one is contiguous, the other is non-contiguous. So an array is contiguous memory, and a list is non-contiguous memory. Now, there's other functionalities associated with one and the other that set them apart. There's things you could do with one that are not done the same way with the other, and we'll deal with that in the different exercises. And you'll see it, you really see it, some of the exercises we'll do here in Module 9. So we'll talk about the two most common list implementations, and that's arrays and linked structures. Now, when I say arrays, it's an array, and for whatever reason, the author likes to kind of call an array a list, and they are similar, but they are not the same. All right. So let's talk about lists in a way that we'll look at it from the standpoint of linked lists. All right, the first item in this list is going to be the head of the list, and the last one, we'll call it the tail. And by doing that, this list class that we're going to create objects of, or we're going to instantiate this list class, it's going to have functionality associated with it that references the head and the tail. So we'll just keep in mind that it's sequential in structure, but not sequential in memory, so it's not contiguous, at least in this context, and it really doesn't matter if it's contiguous or non-contiguous for what we're doing now. But structurally, we will have a head and a tail, much like a train has an engine and a caboose. Think about it like that. So with that said, the length is how many cars do we have? All right. Well, we start counting with 1 to count the length. And if I had 10 cars, including the engine, if we had 10 cars in the train, they would have an index of 0 to 9. And if I wanted to access the last car, that would be len minus 1, and that would give us the index of that last car. Now, these are concepts that you should have dealt with back in C# or back in intro to programming. So our indexing starts at 0 and proceeds from there. And len minus 1 is the index of the last item in our list. Now, talk over and over again about physical memory and logical memory. Now, when I say memory, I'll just say space. Let's look at it that way. Physical space and logical space. So logically, I can have, and I'll talk about it in different exercise videos. I've probably talked about it in previous lectures as well. But we've got to drive this home in a way. So the size of the list is how many positions are occupied. When we talk about the size attribute, that's how many positions are occupied. The len, also how many are occupied. Now, we can also look at the logical memory, and the logical memory is how much space have we reserved to be available to us. And we'll deal with that in a couple of exercises where we have to look at how many items do we have, and if we've reached capacity, then we need to increase the logical memory by 100%. So if I had something with a length of 12, we will increase the logical space to be 24. Conversely, if we are using half of the available space or less, or I should say if we're using less than half, we will cut the logical space down. So we don't want to have more space tied up than we really need. And we'll programmatically go in and manipulate that logical space. And we'll also say what the physical space is. Now, with that said, we've got common operations that we'll deal with. Add. Now, it depends on the structure we're dealing with, but for this, look at it as we're dealing with a list. All right. Could be a queue, but for the most part, we're dealing with a list. Stack, this is not going to work. So traditionally, if we add an item, we add it to the tail. If we insert an item, we need a position to insert it to and the item we're inserting. If we're replacing, we need to know what is being replaced and with what. If we're going to pop in this context is we're going to remove something from a specific position. Now, up to this point, if I popped a stack, all right, it came off the top. If I popped a queue, it came off the front. This pop on the list removes it from wherever we want it removed from. So this is the parent class that we're going to use for other structures. Well, with that in mind, as long as we know the rules to the parent class and we know the rules to the structure that we want to apply it towards, then we know how we're going to go about doing things. All right. So we've got two different ways to look at things. One is index-based, to where we're manipulating based on a specific index, or there's another way to look at things, and they talk about it as content-based, a search for some value being stored in the list, and we're searching by value, not by index. Okay. So with that said, I'll have an instance of a list. We'll call it a big L. L.insert, pass it the item, or the index and the item. L.pop, what is the item or the index on this, has a default value of none, or we pass it some value. On this one, it's L.I will return the item at a specific index. And this is L, I shouldn't say L.I, L of an index I, L of an index I equals item, you assign that value to it. So these all are indexed based. Okay. Now, if we come over, we want to add an item. Let's go into the tail, remove an item. We're removing it based on its content. Okay. And we'll go find it and take it out. Now, you'll see in some of the exercises, we have a precondition, and the precondition is that it exists. Now, it's an assumption. We're not going to assume that it exists. We're going to test first. Test to see if it's there. Now, if it's not there, we're going to throw an item, or throw an error, and it's not in the list, or it's not in the queue, or it's not in the stack. All right. If we want to find the index of a specific value, we need to find out that it's there first. And if it's not there, we throw an error. If it is there, we return the value. Okay. Both concepts that are all three concepts that we will deal with in the exercises in this module. Okay. So an iterator. Iterator itself, it's a method that will allow us to go through the list itself. In some of the exercises, we'll use the term backing store. So you'll see it in there. Now, one of the things that we want to find out about a list, and there's functions that we're going to create in those exercises, is does our list have a node that follows? Whatever node we're on, is there a node behind it? Is there just one node, or is there a node behind the node we're looking at? All right. What is the next node? Is there one in front of it? Now, this has previous. This is where it gets a little funny, and if we're talking about a traditional linked list that is a singularly linked list or a doubly linked list. Traditionally, if we're talking about has previous, it's in a doubly linked list, and there's a pointer to the item ahead. Check to see if there's an item ahead. If there's not, then that means we are at the head node. If there is no next, we are at the tail node. We could be at both the head and the tail, meaning there's only one node. Okay. So, like I said, different functions that we're going to deal with in the exercises. We're going to do insert, and on this one, it's a mutator function. We've got a list, and we want to insert in that list this item. By default, it will go to the tail. If I want to remove something, it's going to do one of two things. It's going to remove the most recent or whatever I pass to it. So if I don't pass it anything, it's potentially going to pull the last item. If I pass it something, it's going to pull that item and then essentially move everything that follows it ahead a position. Now, all it does is changes the pointers on the nodes that are connecting or referencing each other. Now, to replace an item, we'll have to go find that whatever it is, and we need to replace it with something. So it's more stuff that we're dealing with. And that's, like I said, we're dealing with them in the exercises. Okay. Now, current position traditionally deals with the node that we're on or the index of the node that we're on. Okay. And sometimes it would be an N or an I. First is the first node, last is the last node, and we'll have functions that reference first and last. So we've got some code here. They say this code illustrates the use of the list iterator. And using the list iterator will define a list from 1 to 9. And it's from range 1 up until 10, but not including 10. So we've populated it. It has that size. Say, what's the length of it? 10. Print the items from first to last. It's going to print whatever's in there. Print the entire list. And if I wanted to create a list and use a list iterator, then so you know what? I want to create an instance of this list using the list iterator, and I'll call it a list iterator. And I say I want to print front to back and list iterator dot first will return the first, whatever's in the first position. And while list iterator has another node, go through and print what's next. And then print what's after that. And then print what's after that. And now that's as long as there is something next. So we do that test to see if there's something next. If there is, print it. So this validates that there is something to print, and it avoids us trying to print when there is nothing there. We can go do the other direction, go backwards. So print the first, print the last. For count in range 2, list iterator dot next, and we're going to insert in the 10th position. Print the list. We're going to remove 2. Boom, boom. So this is all pretty straightforward. Test to see if there's a next. If there is, let's go deal with it. And then we'll remove it. So on this one, we're going to remove all items. We'll go get the first one out. And then remove all the rest of them. Just one right after another. Okay. And then when we're done, the length should be 0. Here's the outputs for each thing. Right. Like I said, we'll deal with all of these in the exercises. So we've got index-based operations, content-based. So that's based on the item itself. This is based on the index, I. And then there's positional-based operations, meaning is there something in front of it, something behind it? We'll deal with what's in the very front, what's in the very end, the one that's next, the one that's previous. Remove a specific item. So those are based on the operation itself as being position-based. Right. So we've got the traditional functionalities that are built in that we've dealt with over and over again, and we will continue to deal with them over and over again. And we'll have a few more that we'll deal with, and we get used to writing these over and over and over again. But they're not always the same depending on the parent class that we're dealing with. So if we're dealing with a list, these have to be written a certain way. If they're dealing with an array, they have to be written a certain way. And we see that in the different exercises. Okay. Now, we've got to always be aware of preconditions. The first precondition that we want to deal with is the isEmpty function. And I could just use the isEmpty function to go look and see, is there anything there? And if isEmpty returns a value of true, I don't want to proceed because there's nothing there. It is empty. So we talk here about heap storage management, and we dealt with stacks back in 7. And stacks and heaps are similar to a degree. One of the applications, I should say, that we can use relative to the structures we're dealing with. Let's say a linked list. All right. So a linked list points to the location of the next piece of data and where it's stored. And we deal with these structures in the way the computer runs. The computer runs in a stack. So we use a structure to manipulate the stack of operations that are being addressed. And that's first in is the last out, or last in, first out. It's both the same. Now, in memory, we'll have different tracks on a disk. Now, this is kind of old school because now we're dealing with different types of drives, and we're not necessarily dealing with an HDD. And this is, we're looking at an HDD and in the way it's set up logically. So we have tracks and sectors on the surface of a disk. But in solid state drives, it's not set up this way. It's similar, but it's not necessarily set up this way. In either case, we have positions and we store things in random locations. And we need to be able to access things that have been stored in random locations. So lists work on a lot of these things, and they work really well because of the functionality associated with the lists. So with that said, we'll deal with lists in the next chapter when we deal with trees and binary search trees. We also deal with it in chapter 11 with sets and dictionaries. And lists are a great structure when we're dealing with, or I should say a great data type when we're dealing with that kind of data structure. So a tree data structure or a set or a dictionary, those things are well suited to using a list as the parent class. Now, we've got what we call an abstract class, and we've dealt with it time and time again already. So we've got an abstract list, abstract collection, and we will use these again in this module. So The collection is, what is it that we're going to group together? It's a collection of data. And then from there, let's go ahead and we're going to narrow it down, and it's not just an abstract collection. We're going to deal with an abstract class. And that abstract class is going to have a constructor, and then we'll have some modifiers and accessors, mutators, however you want to word it. And they're all very typical. Now, these are traditional for a list class. So we've got an abstract list that's what we're dealing with. And up top, so we have this, and we're defining this abstract list class here. So here's our built-in, and then from here, we will instantiate this abstract list and create our own. So we'll get the constructor, we'll get the mod count. So we have another where we'll increment the mod count, what the index is, add an item, and remove an item. Now from there, we could look at the same thing when it comes to an array-based. And we'll deal with different exercises, popping back and forth. Okay, let's do it now with a list. All right, let's try the same thing with an array. And from one to the next, how we write the iterator, how we write the constructor will be different. Okay, much of it will be similar. So we look here, self.items equals array list.default capacity. When we come back over here, it's different. Self.modCount equals 0. So, but then we've got the init here. But then we've got the init here. So they're similar, but not 100%. Okay. And depending on what the parent structure is that we're dealing with, whether it's an array or it's an actual list, we're going to deal with them different. Now, both of them, they're wording them as abstract lists. So this one, we're saying we're taking an abstract list and we're creating an array list. This one, we create the abstract list. So we got the collection, abstract list, and then from abstract list, we go to array list. So each one's inheriting things from the other, but we're having to modify them because the structure itself is different. Now, with that said, we talk about a linked implementation. Things are linked. I'll talk about it in the exercises. I'll talk about it in other videos. We're talking about a linked structure. We'll have nodes, and nodes will point to the location of the subsequent node, if any. And if it's a doubly linked list, it'll point to the preceding node. Okay. Now, we've talked about nodes before. Head is very front. And now here, and this is a doubly linked list structure. Here's our payload with the hash through it. So there's our payload. That's the data. The front has a pointer, and the back has a pointer. The back will point to what's behind it. The front will point to what's in front of it. And if I want to move forward, I just reference the pointer in the front. If I want to move back, look at the pointer in the back. We'll also deal with, in Module 11, a node that has a pointer in the front to the one item ahead of it, and two pointers on the back side, one pointing to the left node and one pointing to the right node. And we'll deal with those in trees. So it's the same kind of structure. It's a hierarchy of sorts. Things have to happen in a sequence. I can't get to the next node without having passed through this one. So here's our node. I can't get to this next node without having gone to this node and looking at the tail end of it to find out where's the one that follows you. Where do I go to get that? So these are two-way structures, and they show an example here that on this one, the front points all the way to the tail. So when you get to the front, it cycles back to the tail. When you get to the tail, it cycles back to the front. So you can loop through it this way, or you can loop through it that way. Now, they don't all necessarily, when you hit the tail, loop back to the front. Some will say, look, you're at the tail, there's nothing that follows us. You want to move back forward, you can move back forward. So they have a pointer in the front and the pointer in the back. And it just so happens on this one, it loops back around so you can start back at the front. So we've got different types of doubly linked lists. And there's a structure on our linked list on how to initialize it and how it's going to be set up where the pointers are going to point to. And it's all done up on the front end. So we'll have different functions. Set item. I need to find out where it is and what the payload is. Where it is and the payload. And this indicates the structure itself because we're dealing with an instance of this parent object. So each one of these will have self in them. Get node, just you got the position or the index and go get what's there. And it's what am I going to get that's there? Now, depending on the structure, it'll be a little bit different from one to the next. The way we've got this written is we use a probe. We'll say probe.next is we'll go look into the next and save it to probe. And then at the end, we return probe. Now, in some instances, I can reference by get node. So get node has an index. Once I've got the index, I can access the data or the payload of that node and assign a value to it. So that's setting an item. Inserting, where do you want to have it go and what's going in it. And this will essentially, we need to know if it's a two-way node or if it's a one-way node. If it's two-way, we need the item, the node ahead, and the node itself that it's replacing. Once we've got the node itself it's replacing, we will point to where it's at on the tail end of what we're inserting, and we will point to what was ahead of it as our proceeding. Now, that node after it, that next one, that's going to end up pointing to us if it's a two-way node. So these things, it's once we visualize it, it really starts to make sense. Now, if I'm talking about time and space analysis for two different implementations, content-based is going to be big O to the N. I have to search the whole doggone thing in the worst case scenario to find it. Now, add method I don't have to go through the whole thing because I've got a function that will allow me to get to it in constant time. I go to that one specific position. So we've got a chart here that compares the two. Get item, if it's an array list, constant. Get item in a linked list, think about this conceptually. If it's a linked list, it's like going from one train card to the next to find what you're looking for. And it says, go get to, you start at the beginning of the train, get to car number 34. And I've got to go through all of them just to get to car 34. On an array, at the beginning of it, we know where that index, it's all contiguous memory. And the array list will let us access it by index. Set item by index. On the other one, we have to go through sequentially, and things are having to move back and forth in position, indexes change. So these are just about all in. The only one that's not in is the add item. And the reason it's not in is because it's going to add the item at the tail. The index of the tail is the length minus 1. That's constant time. So that's easy peasy. Insert, it's going to be in because I could be anything. So this one, I may have to push everything back to be able to insert. So there's where the n comes from. Popping something out, I have to move everything from that point to the end forward one. There's our n. Same thing with remove, and same thing with index. So with that said, we've got list iterators that we would deal with in probably half of the exercise, if not more, in Module 9. So it's fairly straightforward. There's only so many things that we can do. We're very limited contextually or functionally when it comes to what we're dealing with here. And the limitations are all we can do is what we've inherited. So we've got functions we've inherited. That's all we got. So the next or previous operation, we need to go verify has next or has previous first. So we've got these preconditions we got to deal with. These preconditions, they exist in most of what we're having to deal with. You'll just get used to dealing with them. I can't remove something if it's not there. I can't. So what do is empty in most of what we're going to deal with. Okay. So different navigational methods. So has next, we're talking about this backing store. We'll see this in about half of the exercises you're going to deal with. And backing store is our iterator and what we're dealing with. So go create the iterator, call it backing store, and what's the length of it, and is the cursor where we're at, is it less than the length of backing store? We've got next, and there's preconditions associated with it. Does it have a next? No. Well, all right. Now we've got to go look at, is the mod count the same or not. You're trying to do something that you're not allowed to do to the iterator. And then we've got the position of the last item. Well, if the cursor's gone to the end, that's the last item eventually. And then we'll go ahead and set the cursor one more forward. It'll return whatever the position is of the last item. So these, like I said, we'll go through these in a number of different exercises. I'll give videos for all the exercises posted in the module overview page. So we've got mutator methods, which are insert, replace, and remove. And when we insert something, everything after it has to move back, unless we're inserting it to the end. And if we remove something, everything after it has to move forward, and the number of things there are mod count. On this one, we're saying our mod count moves forward, but the position of the last item moves in one. So this last item position is how long is it, the thing that we're dealing with. All right, so we'll go design an iterator and a linked list. And there's so much that we deal with. We've dealt with what a sorted list is previously back in module 6. We actually deal with sorting in this module as well, and we deal with sorting in module 10 as well. We'll probably deal with it in 11 and 12 also. Okay. So a sorted list has certain methods associated with it, and things, when they're sorted, are sorted by some value, and that will dictate the position. So it has to be inserted in a certain place, has to be removed from a specific place, and then things move based on their value. Okay. Precondition has to be there before I can remove it. Has to be there before I can tell you where it's at. Has to be there before I can tell you where it is. So it sounds so basic saying it has to be there. But we can't assume anything is there, because if we assume it's there, try to go get it, and it's not, then we're going to get hit with an error. I want to set values. I want to insert, find out what an index is, add something, and use a list iterator. Each of these different list classes that we're dealing with, whether it's an abstract list, an array sorted list, or an array list, they have different types of functions, because the structures that we're dealing with, the functionalities have to be performed a little bit differently for each one. And we'll go through it time and time again in these different exercises. And they'll look just like this. If there's precondition, we'll have it listed. And then we'll work our way through navigating what that precondition is, and then assign whatever index that item. So is there room to put it? Somewhere to put it? If there is, let's go put it there. So if you said, hey, put this in item number 10, and it was only 5 long, list the item out of, or list index out of range. It's the other way around. If it's 10 long and say put it at 5, we got past this, and it went and did that. Overwrote what was at 5. So these are fairly straightforward and things that we've dealt with before. Some of them just reference other um, other classes and the functions that are in them. So this add method uses the abstract list add method, and you just pass itself an item. So this method, all it does is calls another method and it's almost like it's outsourcing the work. It's the best way to look at it. Okay. And we'll see a bunch of that in what we're dealing with. Now, some of the functionality, some of the methods that we're going to deal with are going to be recursive. And you'll have these methods that call themselves. Lisp is one of them. And essentially, as you're going through the nodes, and we deal with it in Module 10 as well, we go through one node at a time, and the same thing that I did here, I'll do it again. So I'll just, once I'm done with that, rather than having this long sequence of statements, I'll just recursively go back into the same method over and over and over again until I'm done. And I'll just have a way to get out of it once I've met a certain condition. Okay, so here's a good example of contains. Is it empty? That's the precondition. Boom. It's not. Is the item the first one? If it's not, let's go see, does this list from that we're dealing with, this contains, we'll pass it item, and then rest list is everything else beyond the first item. So I check the first item, and if the first item is it, yeah, it's there. Well, it's not the first item. Let's go look at all the rest of them. And it recursively goes boom, 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 right on through it, calling itself, calling itself, calling itself. Same thing happens here. Calls itself, calls itself. Same thing here, length, calls itself. This helps us save time when we're talking about big O notation. So we recurse as needed to do whatever it is we're going to deal with. So we will deal with constructor functions, or we'll call it cons functions. Cons AB is first. Is it equivalent to A? Cons AB, rest, is it equivalent to B? So let's, I don't know if we've got one here. No, they don't even show us one. But I've got it. We walk through it in the exercises. And here we go. Here's one. So here it is. Comes in the data and the list. Returns a list whose head is the item, whose tail is list. There's our cons, and that's list, and this is actually one of the exercises towards the end of Module 9 we'll deal with. Okay. Now, we can print, depends on the IDE that we're dealing with. we don't have that set up in this, but we do use this method, and it's in the node class, and we can do that. So we've got that option. So we've got the ability to create a list, a certain length, and I can remove something out at a certain position. We don't deal with this so much in the exercises, so that was just a little bit at the end that we're not actually going to apply so much in the exercises. All right. So with that said, this one's the list. We deal predominantly with doubly linked lists in this module in the exercises. Okay. So I'll see you in those exercise videos. Keep up the great work.